Hey everybody. If you're watching this video, hopefully it is video two of two. The first one was the permutation video. If you haven't watched that one yet, I do suggest you go back and watch that video first, just because there's a couple of things like factorials and counting principles and even permutations that I'm going to use while making this video. So if you haven't watched the permutation video, stop this one, go back, watch the permutation one, and then come and watch this one second. Okay? So, in the last video, we talked about permutations being a way of quickly calculating the number of outcomes when we are picking objects from a group, but more specifically, picking objects from a group in a way that order matters because there are situations where order does in fact matter, but there are some situations which order will not matter. And when that is the case, we will be using combinations instead. So a combination is a selection of objects without regard to order. So examples of combination or examples of permutations, like in the last video, were something like uh, the number of ways of organizing the winners, the first, second, and third place of an eight-person race, where the same three people could win, but they could win in different orders. Right? So order matters in that case. Picking a committee of president, vice president, treasurer, right? In that case, order matters because even if it's the same three people, if they have different jobs, that's still a different arrangement. For a combination, though, examples of this would be picking five fruits from a possible eight to make a fruit salad. If your five fruits are apples, oranges, bananas, pears, and watermelon, it doesn't matter what order you pick those fruit in because you're going to have the same fruit salad no matter what. Choosing four people from a group of 10, again, doesn't matter if you choose person one, two, three, four, or four, three, two, one, it's still the same four people. Three colors from a color brochure, the same thing, right? So when we're using combinations, we're looking at situations where order does not matter. So how does that change everything? Well, let's take a look at an example question, and then we'll take a look at how combinations change as opposed to permutations. So the St. John High School Physical Education Department has three free passes to a school hockey game to give away. Amanda, Brendan, Chloe, Daniel, and Emily are all interested in having one of the free passes. How many ways can the Phys Ed department give away these passes? So with the previous video, what we would have determined is we would have said, okay, well, that would be five. So determine how many ways they can select three people in a particular order from a group of five, right? So with the previous video, we would have done a permutation because that's what we learned. But with this case, permutations aren't going to work. So if we were to just pick three people from a group of five, then it would be five different ways of giving out the first ticket. We could give it to one of the five people. But then once the first ticket's given out, there's four possible ways of giving the next ticket. And then once that ticket's given out, there's three possible ways to giving the last ticket, or in total, there's 60 possible ways of arranging the three tickets. Or, just like last video, 5P3, where this is a permutation, ways to select three people from a group of five if the order mattered, right? So if it mattered, like let's say it was just a cluster of tickets, didn't really matter which one you got, but let's say the tickets were better, like one ticket was the best ticket, and one ticket was like up in the lower bowl, and then one ticket was way up in the upper bowl, right? Then order might matter, but in this case, order doesn't matter, so we have to be careful. But consider the following possible selections of three people. So let's just consider one possible selection. So let's say, for example, tickets were given to Amanda, Brendan, and Chloe. Well, is there any difference between giving tickets to Amanda, Brendan, and Chloe versus giving the tickets to Amanda, Chloe, Brendan, or Brendan, Amanda, Chloe? And the answer to that question is no. So what ends up happening for these 60 possible ways, we end up with a number of repetitions. And what we want to do is we want to make sure that we're not counting those repetitions more than once. So this is why we have something called a combination, because what a combination will do is it'll take a permutation and then it will cancel out the repetitions. So these groups represent six of the possible 60 permutations of the three students from five. They represent only one possible combination of the three students from five. So even though this group represents six permutations, it really only represents one combination. Similarly, every other possible combination, three from five, would be represented in six ways, six different permutations. So what that means is if our three three, sorry, not three. Um, if our 5p6 here is how we got these 60 possible, sorry, 5p3 is how we got these 60 possible outcomes. Each outcome, each permutation can be represented in 6 different ways. So that's to get our combination. So what we're going to do is we're going to take the number and divide it by 6. Similarly, every other possible combination of 3 to 5 will be presented in 6 different ways as permutations, so the 60 permutations would have to be reduced by a factor of 6. Now, 6 is 3 factorial, and it's not a coincidence that that 3 factorial that we have here ends up being the same number of tickets that's being given away, right? That 3 is not a coincidence. So to obtain the possible number of combinations, what we're going to do is we're going to take the possible number of permutations and divide it by, second, leave us a little bit to work with here, and divide it by 3 factorial. Possible number of permutations and divided by 3 factorial. Or in other words, 5 factorial divided by 2 factorial divided by 3 factorial, or 5 factorial divided by 2 factorial times 3 factorial. This is a combination where we're taking that permutation and we're canceling out any repetition. So how many repetitions are there going to be? There's going to be, for every permutation, for every group of 6 permutations, that's going to be 1 combination. So there's going to be 6 times fewer combinations, right? So then that's what we're dividing by this 3 factorial. And in this case, we get 10 possible ways of giving out the 3 tickets. So there are 10 ways to give out 3 passes to the 5 students. So here is our formula for combinations. You'll notice that the formula is actually just the same formula as permutations with one slight difference, right? So this part of my formula right here, that is a permutation. This is NPR. So then what's happening is we're taking those permutations and we're dividing them by R factorial. And the reason, again, we divide that by R factorial is because that R factorial is going to be the number of repetitions per permutation. So the notation NCR is used to represent the number of combinations without regard to order, or of our n items taken from a set of n distinct items. So with the previous question, if now that we know what a combination is, we could have gone through this question by just saying, well, we have 3 passes to give to 5 people, so it's 5. Order doesn't matter, C3, and we can just plug that into our formula. So let's take a look at another example. If a pizza can have 3 out of 7 possible toppings, how many different pizzas can be made? So here, it doesn't matter. So I have 7 toppings, so they could be anything, pepperoni, mushroom, peppers, whatever the case may be. But I have 7 possible toppings, but I want to make a 3-topping pizza. So again, what ends up happening is if I were to make a pizza that was pepperoni, mushroom, and green pepper, right? That pizza is the same as a pizza that has mushroom, green pepper, can't spell today, pepper, and pepperoni, right? It doesn't matter what order the toppings go on because once you put on the 3 toppings, you're going to have the same pizza as long as the toppings are the same. So with that in mind, this is a combination question because it doesn't matter what order the toppings go on. So what we're going to do is we're going to find the combination of 7 choose 3, and then we can just use our new formula. So we get 7 factorial divided by 7 minus 3 factorial times 3 factorial, which is 7 factorial divided by 4 factorial, 3 factorial. And if we're simplifying this a little bit, 7 times 6 times 5 times 4 factorial. So 4 factorial and 4 factorial will cancel, and we're just left with 3 factorial, which is 6. And 6 divided by 6 leaves us with 7 times 5, or 35 possible pizzas if we're picking 3 toppings from 7. Okay. Now, what's going to end up happening is sometimes we might be given a situation where here's a combination we want you to solve, but here's something that needs to happen. So some constraints. So let's take a look at this example. For a deck of 52 cards, a 5-card hand is dealt. How many distinct 5-card hands are there if the Queen of Spades and the 4 of Diamonds are included? So before I add on the constraint, let's just stop the question. How many distinct five-card hands are there? And we just stop there. If I were to ask you to solve a question like that, what it would be, it'd be 52 possible cards for the first one that's dealt, and then 51 for the next one, and then 50 for the one after that, and then 49 for the one after that, and then 48 for the one after that. Now, we have to be careful because, again, this is one of those questions where order does not matter. If you were to get the ace of hearts, the two of diamonds, the three of clubs, the four of spades, and the nine of hearts, it wouldn't matter what order that they come in. So again, this doing the question like this is a permutation. So we'd have to be careful about that. So what we could do to find the total number of possible cards that can be drawn is we would do the combination 52, choose 5. And that would tell us how many 5-card hands can be drawn from a deck of cards. So that would be our 52 factorial divided by 52 minus 5 factorial and times 5 factorial. So we get a relatively large number here. But if we use our calculator and solve it that way, so 52 5 is 259,890. 2,598,960 possible arrangements of 5 cards being drawn from a deck of 52. Now, once we know that, if we take a look at the next section, it says if the queen of spades and the four of diamonds are included in the hand. So now if I think about my possible hand here, right, 1, 2, 3, 4, 5, what we know is that the queen of spades, gotta think what a spade looks like real quick. Queen of spades, I think it looks something like this. And the four of diamonds are included in my hand. Now, how many possibilities? So again, with a permutation, what we'd have to do is we'd have to consider if order mattered, well, how many ways could I arrange the queen of spades and the four of diamonds? And then how many ways could I take that group and arrange it into my group of 3 here, my group of 4 at that point? So then we'd have to do a bunch of extra steps. But with combinations, again, where order doesn't matter, we can just kind of forget about this. Now, all we need to do is figure out, well, how many cards or how many ways can we get these 3 spaces filled? So that's another combination. So we're choosing 3 cards now, but we have to be careful. We're not choosing 3 cards from a deck of 52 anymore. If we're saying the queen of spades and the four of diamonds have come out of my deck, now there are 50 cards left in my deck, so that's what I need to do. So 50 factorial divided by 50 minus 3 factorial times 3 factorial. And again, if I solve that in my calculator, we get 50 combination 3, 1,960 cards. Sorry, 19,600 different ways of having a 5-card hand where the queen of spades and the four of diamonds are included in that hand. Okay. So let's take a look at a couple of other examples and take a look at ones that have other constraints and restrictions and cases, just like with the previous video. So a research team of 5 members is to be formed from a selection pool of 8 chemists and 9 biologists. How many research teams are possible consisting of? So with these questions, what we're being told is now, well, I want at least 3 biologists, or at least 1 chemist, or at most 2 chemists. So with these types of questions, we have to be careful because there are certain restrictions or constraints that are being added. So, for example, if I wanted to make this group of at least 3 biologists, well, the word at least or at most implies that we're going to have to deal with cases here because we could have exactly 3 biologists, or we could have 4, or we could have 5. So if that's the case, what we want to do is we want to break this down into case 1, where we have exactly 3 biologists, and then case 2, I keep wanting to write cosine for some reason, case 2, where we have 4 biologists, and then we'll have case 3, where we will have a group made up of entirely 5 biologists, right? So there's our possible cases. And then it's just a matter of using our combinations to figure out how many ways there are to arrange that group with these distinct features. And then once we have our three cases, we're going to add them together because this is an or situation where we have case one or case two or case three. So if I know for a fact I already have three biologists, so if my group of five is made up of biologist, 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 right? Then there's two more possible spaces to fill these last two spots. Now, case two is biologist, 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 and there's going to be one more space to fill that slot. And case three is going to be biologist, 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 and a fifth biologist. Now, we have to be careful because we want to make sure that my case one and my case two and my case three don't overlap. Because if they overlap and we add them together, we're going to end up counting situations twice. And what I mean by that is if my case three, or my case one, sorry, if I have three biologists, well, there's a possibility that this is going to be another biologist and another biologist. And if that's the case, then we end up with case five. So we have to be careful about that, right? So we don't want these cases to overlap. So this isn't at least three biologists. This is exactly three biologists for case one, and exactly four biologists for case two, and exactly five biologists for case three. So now, knowing that it's exactly three biologists, what we need to do is choose our three biologists from our group of nine. So this is going to be 9 choose 3 times our two chemists from our group of 8. 8 choose 2. And then for case 2, again, it's going to be 9 biologists, and we're choosing 4 of them, multiplied by 8 chemists, and we're choosing one of them, right? So this has to be chemist, chemist. This one has to be chemist. And then finally for case 3, where we have exactly 5 biologists, we have 9 total biologists, and we want to choose 5 of them. Then once we do these calculations, we're going to add our 3 cases together. So if I do 9 choose 3 times 8 choose 2, I get 2,352. And then if I do the same thing, 9 choose 4 times 8 choose 1, I get 1,008 ways of doing that. And then finally, 9 choose 5 is 126. So then if I take those three cases and I add them together, so 126 plus 1,008 plus 2352, we get a total of 3,486 ways of making this group of 5 scientists that contain at least 3 biologists. So this would be question A here. Then question B, similarly, how many ways are there to make a group of at least one chemist? So there has to be at least one chemist, but there could be more than that. So in this case, instead of saying, okay, well, let's look at all the cases where I have exactly one chemist and exactly 2 chemists and exactly 3 and exactly 4 and exactly 5, what we can do sometimes to simplify our work is to go backwards, to say, okay, well, how many ways are there to make a group with no chemists? Then let's take that number and remove it from the total possible ways of making this group, and then we'll have our answers. So what I mean by that is, how many ways can I make a group where I don't have a chemist? Well, we already looked at that. Case 3 from part A was exactly 5 biologists. So there are 126 ways of making our group with no chemists. Right? So then what I can do now is say, okay, well, if there's 126 ways of making our group with no chemists, how many total ways are there to form our group? Well, there are a total of 17 scientists, both chemists and biologists, and we're picking 5. So 17, choose 5. So again, let's use our calculator. 17, choose 5, and we get a total of 6,188 ways of making this group of 5 scientists from 17. Now, of those 6,188, 126 of them are only biologists. So, what we want to do to guarantee that we have at least one chemist is we're going to take the 6,188 and from it we're going to subtract 126 and we get 6,062 different ways of making groups that have at least one chemist. Okay, and then finally, part C says at most two chemists. So again, what we want to do is, yeah, we could do that. We could break this down into a case by case basis where let's see what happens. How many cases have exactly two chemists, or how many cases have exactly one chemist, or how many of these cases have zero chemists. But consider some of the work we've already done. If we have at most two chemists, so again, let's consider those three cases where we have exactly two chemists. How many biologists do we have? Well, three, right? If it's a group of five, we have two chemists, means we have to have three biologists. If I had one chemist, how many biologists have? That's four. If I have no chemists, that's zero. That's five biologists. Well, let's take a look at what we just did in part A. There's my case where I have two chemists. There's my case where I have one chemist. And here's my case where I have zero chemists. So what that means for part C is we actually have the same answer as A. So at most two chemists, we actually get the same value for C that we get for A because it's actually describing the same three possible cases just in a different way. Okay. So last thing I want to take a look at for this video is solving equations that involve combinations. So here, let's take this thing and express it just as factorials, and let's see if we can't simplify the thing as much as possible. So let's do that. So NC7, so that's n factorial divided by n minus 7 factorial times 7 factorial divided by n minus 1 factorial divided by n minus 1 minus 5 factorial times 5 factorial. All right, a lot to unpack from this. So we have a fraction over a fraction. So what we can do is we can multiply it by the reciprocal to probably simplify it a little bit. So we get n factorial times n minus 7 factorial times 7 factorial times n minus, I'm going to do this right now. So n minus 6 factorial times 5 factorial over n minus 1 factorial. All right, so now let's take some of these factorials and break the larger ones up so that they look like groups that contain the smaller ones. What I mean by that is 7 factorial contains 5 factorial. So let's use that to our advantage, right? N factorial contains n minus 1 factorial. So let's use that to our advantage, right? So n factorial could be rewritten as n times n minus 1 factorial. N minus 7, we're just going to leave it as is for now, n minus 7 factorial. And then 7 factorial is 7 times 6 times 5 factorial, right? N minus 6 is n minus 6 times n minus 7 factorial times 5 factorial, and then n minus 1 factorial. And what we see is that here's an n minus 1 factorial, here's an n minus 1 factorial. Here is an n minus 7 factorial, here is an n minus 7 factorial. And here is a 5 factorial, and here is another 5 factorial. So when I simplify everything, I'm left with n over 7 times 6, which is 42, times n minus 6. Or if we combine them, n squared minus 6n over 42, right? Or if we rewrote this as one fraction, n onto n minus 6 over 42. Lots of different ways to write this. Either way would be acceptable in my opinion, but this is what we would get down to. Okay, let's try one more of these simplifying, trying to solve type questions, just these equations that contain, or equations and expressions that contain combinations. So here, let's solve for n. So again, let's take these combinations, rewrite them as their factorials, and see if things start to simplify. So we're going to get 3 onto n factorial over n minus 3 factorial times 3 factorial. And this thing is going to be equal to n plus 1 factorial divided by n plus 1 minus 4 factorial times 4 factorial. Okay, so here if we simplify things, so we get 3 n factorial over n minus 3 factorial times 3 factorial is equal to n plus 1 factorial over n minus 3 factorial 4 factorial. So now, again, kind of similarly with the last question, what we're going to want to do is start rewriting our factorials in terms of smaller ones. So for example, n plus 1 factorial is going to contain n factorial, right? Here, n minus 3 factorial, n minus 3 factorial, and again, 4 factorial is going to contain 3 factorial. So let's start simplifying these a little bit. So 3 n factorial, n minus 3 factorial, 3 factorial is equal to n plus 1 times n factorial over n minus 3 factorial times 4 times 3 factorial. So now if I take both sides of my equation and I divide n factorial, those are going to cancel. I take both sides of my equation, I divide n minus 3 factorial, those will cancel. And if I take both sides and I divide it by 3 factorial, those will cancel. So when I simplify everything, I am left with 3 is going to be equal to n plus 1 divided by 4. So now it's just a matter of solving for n. So then n plus 1 is equal to 12, and n is equal to 11. All right, so that is it for permutations and combinations. So for this week's content, just like always, I will post these videos along with some questions for you to attempt. We'll have our live session on Wednesday and quiz on Friday. I hope you guys have a great rest of your week, and I will see you later.